Hi, welcome everybody. As usual, lovely to see you all, regulars and new faces. So a special warm welcome to anybody who's joining us on our 17th Open Clock Club and live from York in England. And I think the last couple of weeks we forgot to do our roundup of where everybody is. So our normal housekeeping note before we begin, that these sessions are recorded, and I'll just check we're recording. Yes, we are. So that will go on our YouTube archive channel. So if you want to remain anonymous, then please keep your video turned off. So kind of half the deal here is me banging on about old clocks and repairing them. And the other half of the deal is the live chat, and that is over to you. So let's get that kicked off with a quick roundup of where you all are, because it's our favorite thing to do, to print off the live chat and sort of think about where all our visitors are. So very, very warm welcome. We've got quite a lot to get through tonight, as always, so I'm not going to go on too long, but just a little roundup of what's happened during the week. Big thank you to our Facebook contributors who have been brilliant this week in helping people with their clock repair projects, in terms of talking about tools and many, many top tips. If you haven't already, you might want to come over to Facebook and check us out there. It's full of friendly advice on fixing clocks, so it's good stuff. What else has happened? Oh, we had one of my former master's students, lovely Ken, got his master's thesis published or co-published in Antiquarian Horology. I often mention the Antiquarian Horological Society, and they produce this world-class horological journal. His thesis, by the way, was on the work of Charles McDowell, who made clocks with helical gearing. So if you're into that kind of technical horology, then go check it out. We live streamed on Thursday, and again, we talked about threads then and thread matching in old work. So we looked at screw plates and that kind of thing. That was good fun. You can check that video out, although it's like 2 hours long, so it's a bit of a marathon, which is on the other channel as well. And we attended a lecture given by the AHS, and that was by the Swiss academic Sandrine Girardier, and she was talking about Jacques Dreux, so the automaton maker, which is kind of allied to something that's pretty close to my heart. So again, great value this week from Antiquarian Horology, and great value from people who follow us on Facebook. So thank you very much. Now, 2 weeks ago, you may remember that we tried to straighten a pivot on a Smith Enfield clock, and the pivot snapped off, which is often the case. So this week, we're going to try, attempt to make a little drill and then drill out the pivot, find the center and that kind of thing. So as they say on YouTube, let's jump into it. Oh, the other thing that happened this week, which I'm duty bound to tell you, is that we started doing our one-on-one tutorials, sort of paid for tutorials. So if anybody's interested in that on French clocks or Enfield or long case clocks, then get in touch and we can talk about it. Anyway, so out of the way with that, and on to our pivot. So here it is. Let's just move across like that. So we've luckily, the pivot is on the pinion end of this arbor. These Smith Enfield arbors are not hardened at all, I don't think. They're pretty soft, which is kind of quite useful because it means we can drill without annealing, and also we can drill with homemade drill rather than using tungsten carbide or letting the arbor down. But the main advantage of how this is broken off is work holding. So if you've got access to watchmaker's lathe, you can hold it like this. And really, that is the major challenge of re-pivoting. Well, in fact, there are two challenges. One is finding the center. So one is drilling a hole in the middle without the pivot wobbling about. And there are little tools you can buy for that, but TBH, it's probably easier to do it with a graver. But the main thing is work holding. Once you've got the thing held concentrically, then you're kind of like halfway there to getting the job done. So it's going to be easy for us today because this arbor is parallel. If can you ask whoever it's to mute or mute everybody? You can find them. And so if this was a 19th century or 18th century clock, then the arbors are tapered, which makes life a lot difficult because you can kind of hold one end here, maybe in a collet, but you can't drill because the whole thing is kind of wobbling about. So we'll talk about work holding maybe another time. Well, that's the big challenge. But here we're lucky because we can hold this in our watchmaker's lathe collet. So we're going to make a drill. I think it was Mark a couple of weeks ago said, why do you want to make a drill when you can buy one? Well, that's a really, really good point. And there are advantages and disadvantages to both. Making a drill is quicker than buying one in the sense that if we had to deliver this clock to our client tomorrow, let's say, for instance, we can make a drill. Hopefully tonight, we'll see how that goes. And we can just do the thing and get it out of the way. If you buy a drill, of course, 0.7 millimeters, I think this is, it's a bit more expensive per se, but it costs a lot less in time. So you will be able to figure out the business model for both those options. But the reason we're making a drill here, of course, is because we're interested in learning skills and we're interested in material manipulation in particular. So again, we've done a bit of hardening and tempering. We did that last week with the pallet face, and we're going to do it today again with our drill. And of course, if you make a drill, it kind of gives you a bit of a confidence boost if it works, because you can say, I can make a drill. But importantly, those skills are transferable for many, many other processes. However, doing it live, of course, is asking for trouble. So there we go. Let's get on with it. Can I just stick those out of the way? Thank you. So I think, as I said, this pivot is, let's just turn on our MITU. What's that say? Yeah, so it's very fractionally over 0.7 of a millimeter in diameter. So there are a few ways of doing this, and it's good to have options in your armory, of course. That's what these sessions are about, really, because we're kind of interested in repairing clocks, but we also repair lots of different things around the, I've got notes there. Oh, excuse the paper. We've got lots of different things around the house or in other parts of our work or professional life where we can think, we can use this, and it's incredible how useful clockmaking is. So here we've got our arbor like that. It's got a little shot of chamfer on the end, and it used to have obviously pivot sticking out, something like that, parallel, not tapered as I've shown it. But top tip, historically, I see on other forums sometimes people say, oh, that clock had tapered pivots. So I filed them, whatever a pivot file is, parallel, and just hold it there, because if you're looking at work like that of John Whitehurst of Derby, sometimes those clocks have tapered pivots in the back plate, which kind of pushes the mobiles onto the front plate shoulders. So just before you go filing the tapered pivots parallel, if they're tapered in this way, then just think, actually, were they made like this from new? So our pivot broke off, or whatever happened. So obviously here, what we need to do is we need to find the center. when I say find the center, I mean, what do I mean by that? I mean, use a graver to make sure that the hole we're going to drill is concentric with the work. If we put a new pivot in and it's wobbling about, it's not concentric, then the problem with that is the arbor's going to run fine because the run out or whatever they call it isn't going to be much. But in this case, remember, the pivot's right next to a pinion. If it was on this end, we might get away with a little bit of eccentricity, or quite a lot of eccentricity, frankly. But on this end, we won't so much, because any eccentricity is going to affect depthing of this driven pinion and driving wheel. So we find our center, and then there are a couple of ways of going about this. One of the beauties of making your own drill out of blued pivot steel is we're going to try, and again, this is all a bit sort of live. So we're going to try and drill a hole and use the same material to make our pivot out. I've got a question coming in. Would you aim for it to be the same size or slightly bigger than the old one? This one. Yeah, a question from Jeremy about this pivot diameter. Would you want to aim for it to be in the same size, or a bit bigger, or a bit smaller, or whatever? Well, the first thing I would say there, Jeremy, is, do you think it's original to the clock, or earlier and functional and that kind of thing? Now here, where you've got the pinion, what you've got to be a bit careful about in some older work is the roots of the pinion leaves are cut very, very close to pivot diameter. So if you drill out and push a new pivot in, then they sometimes split. Now you can get round that, which is what I'm going to show you in a minute, by getting a bush or a bit of bushing wire and broaching out from the inside and pushing it onto the pinion before you drill out and before you push the new pivot in, and that will kind of hold the whole thing together, at least until you've got the pivot in. So I'm going to aim for the same diameter. I'm not massively convinced that pivots wear down so much. I mean, you do see those that are really mushroomed, but in this case, I'm going to kind of aim for the same diameter. 0.7, if it's 0.7, I don't know. I mean, I'm happy with it being a bit bigger because it's going to be as strong or a little bit stronger. Not so happy with it being smaller because also then I'll have to rebush the hole, which will mean removal of material. So maybe fractionally bigger and broach out, if anything. And as you say, Jeremy, if the pivot's already worn, then you're kind of compensating for that. Here, we can look at the other end of the arbor. And of course, with it being an Enfield, and there are quite a few of these clocks around, we can also measure other clocks and see what that would have been. So there are kind of two ways of going about this. You can drill out, if you've got meat, oversize, and then put a stepped, so with the plug would look like this, and then you would cut down the pivot after to be smaller diameter. Or there are circumstances, as I just described, where you've got a pinion and you can only drill out smaller diameter. So you drill out smaller, and then you put a plug in that's actually bigger. So there are all sorts of options available to you at this point. Now, obviously, this option here is not going to be that strong, or in relative terms anyway. This is quite good if you've got lots of meat. And if you're using, the beauty of making a homemade drill, of course, is within reason, we can make it what size we want, he says rather glibly. So we're going to try and find a bit of blued pivot steel that's about 0.7 and put in a pivot that's 0.7. Let's see what material we've got. I'm pretty laid back about it. If we have to put something in that's slightly bigger, then with turning, if you've ever turned, if you've got a lathe and you turn, it's kind of easy if you're taking a good big chunk off. But if you're sort of mucking about on the surface, it can often be difficult to just take a tiny, tiny weeny bit off. So you'll end up grinding or stoning it down to size. Now well, let's see how we get on. So I'm going to try and make the drill out of the pivot material. Now, if you drill, the way we make the drill, there's a whole video on this, by the way, so I'm not going to labor making the drill too much. It's on our YouTube channel. Please go to that. I think, yeah, Open Clock Club team has put it in the live chat here. And you have to make the wire smaller in the first place. If you drill with the same sized material, when you make the drill, the point is never exactly in the middle. So it actually drills slightly oversized and you'd end up with a wobbly pivot. But anyway, let's get into it. So somewhere, I've got so much stuff prepared today. Well, oh, there we go. So we've got our blued pivot steel. There was a nice little thing on Facebook today where one of our members was talking about blued pivot steel, and you can still buy it. I don't know if you can buy it new or not. Can you buy it new? That's a good question for you to put in the live chat. A good answer, I mean. But you can still buy old stock from poor old retired and deceased, regrettably, clockmakers, and in those blue cardboard tubes, which are really lush, and brass wire as well, also in wooden tubes. Right, okay, so in an ideal world, we'll find a piece that's 0.7. So straight away, we've got a piece that's 0.8. So that's a beginner's luck. That's 0.6, isn't it? Yeah, 0.61, that's too small. So I'm going to ferret about in here a bit. What's that piece there? That looks something like. Right, there you go. Bish, bash, bosh. Gosh, that was a bit of good luck. Anybody would have thought I'd practiced. So if you are not familiar with this material, it's hardened and tempered to blue, hence the color. The blue is only a result of the way that it's been heat treated. So when you heat a piece of steel, carbon steel, and you quench it to make it hard, or even if you don't quench it, in fact, and then slowly heat it, it goes through a range of temper colors, which we talked about in previous sessions. And you can modulate, is that the right word? Anyway, you can manipulate those, the hardness of the steel by stopping at those different temper colors. And we're going to do that today. And it's incredibly useful because you're not reliant on other people. So the question is, and it's now Jeremy's asked that question, that's really kind of put it in the back of my mind. Do we go for 0.8 and then try and turn it down a bit? The beauty of that, of course, is if we've got some eccentricity, we are going to be able to turn it down and maybe get rid of that. Let's just have another little measure up just to convince myself. Yeah, 0.71. I'm going to go with the 0.7. Now, that might be a mistake, of course, because the 0.7, as you can see, doesn't seem like there's much difference in size, but there's actually a lot of difference in diameter when you're down at this kind of, I say down at the scale, big for a watch, but small for we domestic size clockmakers. But the beauty of this, hopefully, is that we can make the, as I said, the pivot out of the same size drill. I'll just keep the 0.8 at one side because, you know, the best laid plans and all that stuff. Now, I don't know if you can see on this because it's quite small, but when the material is, I don't know how this was made, but like sheared or whatever they call it, the end bit is incredibly hard. So I just say, I won't labor making the drill. I'm just going to try and make it quite quickly, and then we can get into actually drilling the hole out. So this, you could try making the drill as it is, sort of with this hardened and tempered material, but I'm going to let it out completely because I'm lazy and I want to do it quite quickly. So to let it out quickly, we heat it to orange, allow it to cool relatively slowly because it's a relatively small piece of material. That won't take too long. So I've got the jacket on that I set fire to a couple of weeks ago. So hopefully it can't get too much more damage. So let's just get some.
So if you can't buy blue pivot steel, what type of steel do you buy?
If you can't buy blue pivot steel, oh, can you hear with that? If you can't buy blue pivot steel, silver steel in bigger diameters is a broadly modern equivalent, although I think it's got other stuff in it to make it into a tool steel. Or piano wire is probably the closest thing, and you can buy piano wire obviously in all sorts of different diameters. So thing about piano wire is I don't know whether it's straight or not, or relatively straight. So that hopefully has cooled slow enough there. Normally what I'd do is I'd trap it in between these two refractory blocks and allow it to cool a bit slower. And you'll have to do that if it's a bigger piece of material. Now with tiny bits of steel, this isn't tiny, sometimes just air cooling is enough to harden it. I think again, Daniel's shows that. So let's just get a file, and no, that's okay. So that softened it, I think, enough for us to be able to work on it. Now I must remember, because I'm bound to forget, to make the end a little bit smaller diameter. So I'm just going to stone the end that we're going to make into a drill, and hopefully that will reduce the size enough. That means that when we put the pivot in, it sticks in the hole. Now I'm just going to go on another walkabout and find my grinding stones. Much rooting about in drawers. Believe it or not, I have actually got organized for this. There's just such a lot of stuff going on. I'll tell you what, in lieu of being able to immediately see where I put the box of stones, I'll use one of my new Easy Lap diamond laps, which actually I've used loads in this last couple of weeks, but I've kind of already fallen out of love with them, I'm afraid. But they are here and available, so I'm cheap, so there you go. So let's just stone this down a little bit. You can see, stone this down a little bit. Now, of course, I'm not going to measure this, but all I need to know is that the drill is going to make a hole that's fractionally smaller than the wire. So should have practiced, but anyway, there you go. Never stopped me before. I suppose I could try measuring it, but I'm not sure. We're gonna. There you go, down to the end of it's gone down to 0.67 mil, so 0.03. So let's call that enough in the kind of clockmakery way. And then we can now get this thing set up in our lathe. So what I'm going to do, as I say, it's all in that video, so I'm not going to draw it out and everything. So the first thing we're going to do is we're going to make some relief behind the head of the drill so it doesn't jam in its own hole with the swarf and things. We're going to cut a cone on the top of it of about 100 and what's a drill? 118 degrees, is it? Like a jobber twist drill? Anyway, about that, something. Then we're going to file two flats on it to make the kind of relief, the shape of the drill. And then I'm going to stone some actual cutting edges once I've hardened it. So I'm going to do that really quickly. And then we'll change the camera onto the lathe when it comes to actually finding the center, because that's the kind of learning here. As I said, the rest of it is all explained in the video, so I don't need to go over it again. So just get our lathe. So this is bog standard 8mm, bit wobbly, watchmaker's lathe. 20mm D-bed, interchangeable parts with other similar kinds of makes, and So we've got 0.8 millimeter. Call it there. You can see that. And first thing out, you can just about see that little witness mark where I filed it. Now the file I've chosen, of course, is quite coarse, so probably not a great idea. But let's just, that cone at the front, we're going to stone that anyway later on, so I'm not particularly fussed about that being super smart. So I'm just going to put my file at 90 degrees. Anybody come up with the answer yet, Rachel? What's the angle for a twist drill at the top? 118, I seem to remember from my, what's the standard angle for a jobber drill? I think it's 118, but I forget. Jobber drill, you know, like a regular twist drill. So I'll just stone it just because it'll be a bit squidgy. Cool. Right, okay. So the next thing is I thought I discovered the complete answer to all my problems in life. And of course, like all these things, they never are. And they are these things here. They're tungsten carbide pyramid cutters for engraving. And I was looking for a pyramid shaped cutter. And so I went on eBay looking for one that was pre-made. I don't know why I didn't just make one, in fact I did in the end, and found these things. They come in all sorts of different angles, and they're for CNC engraving machines. And I thought this is like the answer to my worries on engraving, because you can use them as a graver. Top tip, if you've got access to a diamond wheel, when you drill with tungsten carbide drills, or like micro drills, they always break off, you know, not immediately, but eventually. So turn the drill round and use the, if I can get the bit of plastic off, use the stub end of that drill to make a grinder, to make a graver, sorry, on your diamond wheel. Really, really good, useful source. Getting the plastic badger off, of course, is the most difficult part. And so I saw these things, and they come in all sorts of different angles. And I thought, well, I'll buy a box of assorted ones. Oh, there you go. So there we are. So there's the whole thing. It's like a tungsten carbide PCB drill. It's 1/8-inch shank, and it's got this amazingly useful 3-sided cutting thing on it. So I thought, perfect for this, for finding the center, because that's what you want. And I thought, great, I've got my easy lap diamond things, but it didn't work. And the reason it doesn't work, and it might be to do with the quality or the type of carbide that these things are made from. Because with the diamond cuts well, of course, it's really hard, but it's kind of brutal. So what happens is that it drags material out of the cutting edge. So it doesn't matter how much you kind of grind away. Maybe I need finer diamond. It doesn't matter how much you grind away. You never get a smooth cutting edge. Although saying that, I see that they've managed to do that when they made the thing. So, but they're sold as having a 0.1. Is it 0.1? Yeah, 0.1 radius at the tip. They don't come to a point, because obviously if this was in a CNC milling machine, as soon as you put it in the machine, the tip would break off. And so you've got to sharpen it to get a tip, but then the tip breaks off almost like straight away when we're doing this job. So I spent ages yesterday practicing sharpening, trying to find the center, totally like frustrating. So I put those to one side. Here's the box. They come in all different angles. I can think they're dead useful, but also, like everything, when you think it's going to solve all your problems, it never does. So what I did today was I got a bit of blue pivot steel again and made, so I let both ends down and I filed 3 flats on it. You see those flats? So the same thing, a bit kind of chunkier. And on the other end, I just filed a little angle like that to make a round graver. And then I hardened them like we showed with the pallets and all that stuff, and tempered back to pale straw or brown or whatever color it was, not too soft. So now I've got a double-ended graver. The handle is a sliding handle, which is really useful. So depending on which end you're using, you can push it along a bit either way. So I drilled that and then brushed it out from both ends. And it's a bit of dogwood, by the way, as you can see, cornice. So if you've got that growing in the garden, or even better, your neighbour's garden, sneak round when it's dark, obviously, with your secateurs and steal the dogwood, cut it into 6-inch lengths, put it in the airing cupboard for 6 months, and you've got some really useful stuff. Right, anyway, so I practiced for ages with this, and in the end, I ended up making my own graver, so there you go. So there's a thing for you to do in the week. Get yourself a bit of 3mm blue pivot steel or silver steel and make a double-ended graver. It will be incredibly useful, incredibly useful. Okay, can't remember why I was telling you all that. I'm going to now use the rounded end to generate a bit of relief immediately behind the cutting edge of the drill. Because of course this drill isn't going to have flutes as such. So we need some way for it to not jam in the hole. And the other thing is we're going to drill by holding it in the hand, which is great. But of course, the thing is you tend to get a slightly tapered hole, which is good for us, but we don't want it to be too tapered. So let's just have a wee look. We don't need much. In fact, there's a good chance here this is going to bend and break off. Maybe what I should do is I should stone it. But anyway, let's have a look. I can see T-rest's a bit high. There we go. So I've just put a little bit of wasting immediately behind the head there. I know you can't really see, but I'll move the camera when it comes to the drilling thing. So we've got our cone on, we've got our wasted bit. Now what we want to do is to file 2 flats. Now, luckily, you can see that the manufacturer has drilled the headstock of this lathe, as most lathes, but unlike other kinds of lathes that we might mention, for some crazy reason, and I know you people are all brilliant at maths, John, Rob, I know you're all great at maths, so why have they put 40 holes here and not 60 or 48? Because 60 would have been dead useful. 40 is like, I mean, it's okay for what we're doing, but it's not a particularly cool number, I don't think. So you can see I've put a couple of marks on here, and we're just going to index, put our file on, tip it over a bit. I don't care what this angle is. Turn it round 180 degrees. Tip it up. Now we don't want to file down so the flat comes to nothing. If the flat comes to nothing, then our drill's just not going to have any strength at all. So I'm just going to kind of do it 2 or 3 times and then, oops, then have a little look. I mean, obviously we've got a little bit of sort of time pressure on here, but under normal circumstances, you could do this, have a little look, have a cup of coffee, look out the window, and it's like the most pleasant thing you've ever done, making your own drill. Right, let's just have a look at that now, see how we're going on. Just get a Barry brush. Cool, getting there. So this is just one of those old cutting tool questions. You know, I think broadly, if a tool is pointy and really sharp, it's cuts well, but it's weak. And if it's not very pointy, sorry, if it's pointy and thin, it'll cut well. And if it's like chunky, it won't cut so well, but it'll last longer and less chance of breaking. So that's what I'm trying to do here. I don't know whether you can see, but it's actually quite sort of chunky. So I'm going to just not tip my file quite so much this time. Right, okay, and then let's have a little look. That's actually quite thin, but that's okay. Doesn't look like it's anything like in the middle. Hey ho. So there we go. So I've put the cone on, put some relief behind the head, and filed 2 little flats on it. So the next thing to do is to harden it. So let's just whiz it out the collet and get rid of that stuff. Go back to our mini hearth, get some water. Normally I've got some really, oh, there it is, cold water, which seems to make a difference. Now, remember when you're hardening tiny bits of work like this, tiny, take the heat to the water or the quenching media if using oil or whatever. Don't heat it to orange, move the steel across, because it's the rate of quenching or the rate of cooling that's important as far as hardening goes. So new sparkler's working well. Okay. So now the question is, do we temper that back, as in do we clean off a bit of the steel and then heat it with our spirit lamp? That's Yorkshire rhubarb, by the way. It's National Yorkshire Rhubarb Day, hence my brooch. Or do we just leave it as it is and keep everything crossed that it doesn't break? So if it's not tempered, it's going to cut a lot quicker, but it might break. If it is tempered, it might get blunted. And the problem with sharpening it when it's resharpening is that because we've got that profile behind the head, it's not constant diameter. So if you sharpen back, then the diameter is going to be a bit smaller. I'm going to, of course, risk it and not bother with the tempering process. What do you think, Rachel?
I think risk it, Matthew.
Team Open Clock Club says risk it. Right, so last thing we need to do in making our drill is go to our trusty 1000 grit ceramic stone we all know and love, and I'm going to grind on the 2 reliefs on the back of the drill, which will create our cutting surface. And to do that, I'm going to use a drill with a square collet. You don't need one of these, but it's quite useful because I need to turn, I think I've seen this before, it's engraved R. Miles. I wonder if that's Bob Miles, the electric horology guy. I guess not, but anyway, it's a nice idea. Right. So what I need to do is to line up the flats that we've cut with 2 of these flats on the pin vise. So just need to find my eyeglass. Little bit of a fiddle just getting it lined up. I'll get a pair of pliers, just help me negotiate it into place. How's everybody's a bit quiet today, Rachel?
No, Wilkin said, I don't know if it, but 40 allows wheels of 40, 20, 10, 5 teeth.
Yeah, 40 divisions. Yeah, 20, 10, and 5. But why not 60? Because that would give you 20 as well. It would give you 30, obviously, it would give you 3, 6, 12. Aren't they like more useful numbers? I don't know. It's not a criticism. I just wondered why they'd chosen that when they could obviously choose any number.
Well, you said that too. 60 could give you 12, 10, and 5.
Yeah, so 60 would be a better number. I think, anyway. I don't know. They obviously thought about it. Right, there we go. So I've now got those flats lined up with the square of the pin price. In fact, I better just mark on which flats are the ones I need. So it's 2 and 4. So to create that relief on the back of our cutting edge, if we put our, they can see about there, if we put our drill upright, what we need to do is we need to tip it over a bit and we need to tip it back a bit. Remember to tip it the correct way. So the drill is going to rotate in this direction, in the normal direction. So the relief wants to be, my hand is the kind of grinding, the relief wants to be on that side and on that side, yeah? Okay, it makes sense. Bit of water on there. And let me just get this right. I have to concentrate for once in my life. So put it straight on the stone, tip it over and tip it back. And then I'm going to rotate it 180 degrees, tip it over, tip it back. And I'm mindful that it's going to break off. Right, that's not too much. Cool. So even at this side, we can size, we can see, or within reason, that the center of the drill. Of course, the problem is if the center isn't in the center, the point, it's going to drill oversized. So with this is handmade, it's going to drill oversized, whatever, unless we're in some miracle zone. It actually looks okay. Of course, what I should have done is made one as a stunt double standby. Not to worry. There we are. There's our little drill. Only time will tell whether it'll actually drill a hole or not. And of course, the good thing is, I just thought of another thing. If it drills oversized, we've got that 0.8mm steel to work with as well. So let's get that out of the way. Don't forget to have a break. We need a break. What time is it? 45. 45. Okay. So let's have. Can't actually see the clock. So 45. So let's come back at 48 and resume. I won't keep going, but I'll just get ready for the next step. So a couple of minutes comfort break, back at 48. In fact, that's perfect because I can try and do this thing with the camera. So let's just stop share. How is it?
47.
Okay. Just reshare screen.
Next standard angle for a jogger, 118.
118 degrees, yeah. No person detected. Right, I might just try. So right, okay, so iPhone people, there's an easy way to get the face detect thing off. Presumably I press that little button that says F on it, but that's F stop. Dear me. Anyway, there you go. New camera coming soon. As Davey504 would say, new camera reveal at 10 million subs. There we go. Okay. Anyway, we can see. Forget the other thing. So here's the kind of big challenge of the whole operation, and that is to find the center with our graver. Now, in sort of bigger lathes and engineering, this is relatively easy because what you do is there's a thing called a slocum drill or a center drill. No such small center drill for this thing. You could either make up a little kind of conical guide, like a pivoting tool for watches, but I'm going to try and do it with my graver, which is like every opportunity it's going to go totally wrong.
You take it off portrait.
I don't know how to do it without without turning it off and turning it back on again. It's a pain, isn't it? But anyway. T-rest too high. Hair's too long. So what I've done here is where the pivot broke off, I had the opportunity to file it flat, and I've still got that opportunity. But what I'm going to try and do is do it without that, then we preserve as much of the arbor as possible. However, if I can't get it started, I'll file it. Mm. Right, there we go. So you see what happened. Oops. You see what happened there. When you cut with the graver, it's, if you imagine the graver is under center height, the graver gets dragged away from you. If it's above center height, it gets pushed towards you. And what doing it live. So what happened there was I got the dreaded pig in the middle of the hole, which is a cone in the middle of the hole. Now, sort of rather brutally got rid of it. So we've now got rid of, got to the stage, if I can see it again, where it's running nice and true. So disaster averted. However, practice, practice, practice. Start with the graver nearly flat to the work. Don't put any pressure on it. Don't do what I did. And then slowly rotate it. Then as when you're confident that it's in the center, then push it in. If you put too much pressure on before you push the thing in, then it's going to get that pig in the middle. I got rid of it. But of course, the problem with that is you end up sometimes with a hole that's too big. And in this case, I think the hole is going to, the beginning of the hole is going to be bigger than our drill. Yeah, we might be okay. I mean, it doesn't matter, but you're going to end up with a little line there, which is quite scruffy. Anyway, so start with the graver nearly flat to the work, slowly rotate it without putting any pressure on. And then when you're confident that it's centered, press it in. Because as soon as you press it in, if it's not centered, you're going to be in that position I was in. Now, I'm actually just going to try and reset this camera because it's driving me bonkers now. We've done the most difficult bit. So I'll just stop the share for a second.
Mark said you could put your self-made drill in a tailstock when you watch Maker's Lathe in the centre.
Yeah, it'll wander off the center. Oh, I see. Sorry. Having never done that before, being an old person, my kids would be rolling their eyes, of course. I see what you mean now. There is something called portrait mode. Duh. Right, okay. Got out of that. Let's reshare. At least I can do that. Just about. And hopefully it remains horizontal. Yay, great. Right, okay. So yeah, you can't, unfortunately, that drill is too flexible. As I said, unlike the center drill or slocum drill for a big lathe, you can't kind of line it up with a tailstock. It'll just run off the center. And there, of course, I was trying to be clever, which is always a mistake, by not filing it flat and leaving, it already had a little pimple in the middle where the pivot had broken off. So I could have made my life easier by filing it flat first, but I'm actually kind of pleased because what we've got now are these little marks on the face of the shoulder. Now you might say, well, Matthew, you want rid of those marks because you can improve it. And then of course, anybody who's been to this crazy session before will know that we're not in the mode of improving things. I'm quite interested in those marks because that's how these clocks are made. Okay. So, yeah.
Can you explain what a slocum drill is?
Yeah, a slocum drill, I won't run off and try and find one because I'll never come back, is if you imagine a twist drill like this, regular twist drill, if you look along the end of that, the web of the drill or the actual material of the drill is really quite relatively thin. So it wobbles about. A twist drill is a terrible way of making a round hole. If I'm not an engineer, but engineers will tell you that you always have to drill, then ream or bore or something like that. A twist drill often makes a triangular hole, wobbles like crazy. If you've ever drilled a deep hole in brass or something, then cut it in half, you'll see that the drill goes all over the place. A slocum drill is just like the end of a twist drill, the very tip. Then the rest of it is solid, it's real chunky. And it means that it wobbles less. And when you get the cone that supports the drill, like we did here, you're laughing. Once you get away from having that pig in the middle, you're laughing. So a slocum drill is also called a center drill. What do they call it in the States? Live chat, do they call it a slocum drill or a center drill? Now, normally to lubricate this drill, I'd use spit, but that's totally gross. So I'm just using a bit of glass cleaner. Could do with a little brush actually as well, and some more light, but as long as you can see. So now the second moment of truth, let's see if the drill actually drills. Put a bit of there we are. So I can feel straight away, straight away that it's cutting. So I'm going to faff about a little bit more and actually try and get a bit more light in here. I did practice this, honest. It's just all rather interesting. There we go, that's better. So you might say now, why don't you use the drilling tailstock, Matthew, to line up the drill? Well, there's no need really. I'd much prefer to do it by hand. Now I'm using a pin vise to hold this drill. If I had more time, I'd use a bit of wood, and he'll be free in a minute. He can go now. He can go in 40 seconds. Although of course I'm going to run on as always. I'd use a bit of wood here because this heavy old pin vise thing removes sensitivity, and of course with the drilling tailstock the sensitivity is pretty much gone, even with the lever one. So what I do is put this in a little bit of pegwood and drill like that. Now because we're out of time, I'm just going to drill enough to demonstrate that it actually works, and then we'll just finish off the actual putting the pivot in at the beginning of next week. Otherwise it's going to go on for ages. But let's get the T-rest out of the way. Okay, so I'm going to rotate the drill, and you can see already that the swath
focus.
You can see already that the swarf is coming out, and without sounding too smug, it's even concentric. Without sounding too smug, your drill that you ordered online and paid next day delivery for $7 or $10 or whatever is still in some warehouse, and our job, he says, is going to be finished for the price. It's time consuming, but for the price of a bit of steel. Right, I won't get too excited because I need a little brush to put some, but you can see we're actually drilling a real hole. And I think by the look of it, we just about got away with cutting the center, that because of my rush to get it done and causing that pig in the middle. I thought we were going to see the edge of the cone there, but in fact, it looks like it's we've drilled slightly larger than that. So really pleased about that. Just going to drill a bit more. Any more questions? Rich?
Yes. Does the drill naturally drill straight when the pivot is being rotated, or do you have a very steady hand?
Good question. Does the drill straight? Well, I think the worst that can happen here, weirdly, the drill doesn't wander off. Once you've got that center, when you do this yourself at home or in your workshop, once you've got that center, you can open a bottle of champagne, because that is like, you know, that's a celebratory moment, because the rest of it is just time, basically drilling the hole. So I'm rotating the drill, and again, don't use pin vise like this. This is too heavy and it's kind of really clunky. Use a bit of wood. But I learned this from a guy called John Reed, no relation, and he was head of Rolex in the Far East, and he was drilling out a center seconds pivot for a gent's wristwatch, so about a fifth the size of this, if not smaller, and he just did it by hand. So I thought, well, that's the way to do it. No, it doesn't seem to wander off.
If the tip broke off, would it be curtains for the arbor?
No, if the tip breaks off, unlike the carbide ones, which are difficult to get out, because we're drilling a slightly tapered hole here, because I'm holding it and it's wobbling about a bit probably, you can typically get it off, get the broken bit out. So no, it's not, definitely not the end of it for the arbor. The problem there is if you have to make a new drill, it's getting one that's the same diameter, because remember, we rather liberally just sort of ground it down at the beginning. Whereas again, I do take the point, if you had commercial drills, they would pretty much be the same size. Spit, it's not spit, but spit is the best thing, it's brilliant. Pig spit is really good. If anybody's got a hog at home, then get the pig spit. That's the best drilling lubricant there is. This, I'm using this glass cleaner, so it's basically water with a bit of soap in it as a wetting agent, but it's not as good as spit. I'm not joking, by the way. And spit's kind of free and plentiful. Right, as you can see, little bits of swarf coming out. It's, you know, if you're used to drilling with a twist drill and the swarf flying out, that isn't going to happen with this. You only get these tiny grains. But you can see already we've drilled quite deep, and that's the next question. But I'm going to stop now because we're already running over time. Is how deep is deep enough? I think in our we've already talked about this somewhere. John and I have written something about it. I can't quite remember now, but we kind of came up with a rough formula for how deep you need to drill in relation to the diameter of the pivot. The answer is, within reason, as deep as you can. And because this arbor is quite soft, I'm going to drill quite deep and kind of push my luck, because that just makes seating the new pivot a heck of a lot easier. So I'll have one little more drill. I'll just check. Might sharpen up a bit more. Another key, total key to drilling here is you can feel, the beauty of doing it by hand is you can feel it kind of grinding and biting. The minute it begins to skid, stop, because the drill has gone blunt, and what will happen is the material in the bottom of the hole gets burnished, and then it's really difficult to break through that skin. So if it stops cutting, stop drilling, resharpen. And then my last top tip is that when you restart after a stop like that, start dead slow. And I mean like this slow. If you start fast, you won't be able to cut through that skin. Unless you're using tungsten carbide, of course, and in which case life's quite easy.
It says stud lock or solder.
What for? What, for holding the pivot in? Stud lock or solder? Neither. Hopefully, the pivot's going to be such an amazing fit that we're just going to tap it in. If it's loose, then the old timers used to use oilstone dust, a bit of oilstone dust on just to jam it in the hole. But we could use stud lock, yeah, Loctite. But I'm keeping my fingers crossed that it's going to be a good enough fit not to need that. Well, maybe that's over optimistic. Right, I know we've all got things to do and lives to live, so yeah, you can just see the bits of swarf there. Anyway, so watching somebody drilling a hole is dull as ditch water. But there you go. We've gotten, I think, made good progress there. No disasters. We made our drill. Took what, half an hour to make the drill or something like that. It would have been quicker, obviously, if we were not filming and talking about it at the same time. It's all on the video. Have a look at that, please. And on that channel, if you're not already like and subscribe, then please like and subscribe. We found the center with our three-sided homemade graver. Can't get it in focus. There we are, which is like the most useful tool ever. And if you want to practice this, just get something like a taper pin and just keep turning a center, finding the center, filing it off, find a center, file it off, and so on. Because then you'll be practiced when you come to do it on the arbor. And unfortunately on the arbor, you've kind of only got one chance, because if you get that pig in the middle and you can't go back like I did a little bit, then you're really, really stuck. And this was the other end of the graver that we made to put the relief behind the drill head. So next week, we'll finish this off. We'll drill a bit deeper, put the pivot in, finish the pivot off. Hopefully it won't need any stud lock, but who knows? And then we'll get back to our other clock, which is the rogue tooth, if you remember the rogue tooth. So again, thanks for watching, everybody. Great to see you all. We'll see you during the week on Facebook, and we'll have a great week in the lovely spring sunshine. Thanks very much, and thanks to Team Open Clock Club as well. Bye for now.